Good day students. So in our last class we have seen about SIC XC architecture, and in the previous class we have seen about SIC architecture. Today in our class we are going to see about CISC architecture. CISC. CISC stands for Complex Instruction Set Computers. So CISC architecture have large and complicated instruction set, several different instruction formats and length, and different addressing modes. The implementation of CISC architecture is very much complex. So under CISC architecture, we are going to see about two architecture, VAX architecture and Pentium Pro architecture. So first, in today's class, we are going to see about VAX architecture. So VAX stands for Virtual Address Extension. So VAX architecture is first introduced by Digital Equipment Corporation (DEC) in the year 1978. It was designed for the compatibility with earlier PDP-11 machines. PDP stands for Programmed Data Processor 11 machines. So the compatibility is provided in hardware level, but both VAX architecture and PDP-11 architectures share same machines in multi-user environment. So this is the general introduction about VAX architecture. So now let us see about the first hardware feature, memory. Memory in VAX architecture is of 8-bit bytes. So all are byte addressable. Two consecutive bytes form a word. 4 consecutive bytes form a long word. 8 consecutive bytes form a quad word, and 16 consecutive bytes form a octa word. All VAX programs operate in virtual address space of 2 power 32 bytes. So that is equal to 4 GB. So this virtual address space is divided into two types, divided into two memory spaces. System space and process space. So our system space will contain our operating system, and process space is defined separately for each program. And part of the process space will also contain stack of the program. Virtual memory allows programs to operate as though they had access to extremely large memory regardless of actual memory. So these all about the memory feature available in VAX architecture. So next, registers. So there are about 16 general purpose registers, or 0 to or 15. So all registers are 32-bit long. So among the 16 registers, the register from R0 to R5 are general purpose registers. That is, these registers are used by some machine instructions. Then the registers from R6 to R11, these are also general purpose register, no special functions. Next, the register R12. R12 will contains argument pointer, that is, the register R12 is the argument pointer register, that is, each and every procedure call uses argument pointer to pass the list of arguments associated with the call. Then the register R13, R13 is frame pointer register. So each procedure call convention will build a data structure called stack frame. So the address of this stack frame is pointed by our frame pointer. Then R14, so the register R14 is our stack pointer register. This points to current top of the stack in program process space. Then the register R15, so this is our program counter register. The purpose of program counter is the program counter register will always points to the next executable instruction. In addition to these register, we are having PSL register. PSL is nothing but processor status long word. So this processor status long word states the variables and flags associated with the process. So these are about the registers in our VAX architecture. Next hardware feature is data formats. So as usual in data formats, we will be going to seeing about the integers, floating point numbers, characters, everything. So first, integers. Integers are represented in bytes, word, long word, quad word, etc. Then the negative values are indicated by 2's complement representation. Floating point is represented in 4 to 16 bytes. Characters are represented in 1 byte ASCII codes, that is 8 bits. Then VAX architecture provides 2 different kinds of formats. One is packed decimal format and another one is numeric format. So in packed decimal format, each byte is represented as 2 decimal digits. That is, each byte will represent 2 decimal digit. Each digit is encoded as 4 bits. For example, if I have a number 32, it is a positive number, plus 32. So in packed decimal format, each byte represent 2 decimal digits. So for representing this 2 decimal digits, we are using single byte. That is, each digit is encoded as 4 bits. So we will encode 3 as 0011 and 2 as 0010. Then the sign of the number is encoded as a last bit. So we will usually use the character C to represent a positive number and the character D to represent a negative number and the character F to represent that it is an unsigned number. So since it is a positive number, so this sign will be encoded in the last bit. So in packed decimal format, plus 32 is encoded as 0011, 0010 and C. So this C indicates the sign of the number. Then numeric format. Numeric format is used for numeric value representation. So in numeric format, we are having two types. Trailing numeric and leading separate numeric. So in trailing numeric, the sign appears in the last byte. If it is for example, if the number 53842 plus 53842, the sign is represented in the last byte. So this will be encoded as 53842C. Then leading separate numeric. In leading separate numeric, separate byte preceding the first digit is used for representing the sign. For example, let us take the same example, plus 53842. So this will be encoded as 5384C2. So we will separate the byte preceding the first digit to represent our sign. So that's all about the instruction data formats. Now the next hardware feature is instruction format. So we are using variable length instruction format. Each instruction consists of opcode of 1 or 2 bytes, followed by up to 6 operand specifiers. So that's all about instruction formats. So our next hardware feature is addressing mode. So the various addressing modes available are: first, register mode. So in register mode, operand may itself present inside the register. Then register deferred mode or register indirect mode. So in register deferred or register indirect mode, the operand address is specified by the register. Next, auto increment or auto decrement mode. So here the values stored inside the register is automatically incremented by 1 or automatically decremented by 1. Next, base relative addressing mode. So in base relative addressing mode, the target address is calculated by adding the displacement value plus the content stored inside the base register. Then PC relative, that is program counter relative addressing mode. So in PC relative addressing mode, the target address is calculated by adding the displacement address plus the value stored inside the program counter register. Next, indirect addressing mode. So in indirect addressing mode, the operand is stored in the address of the operand is stored in the memory. So for example, So if this is a memory space, so first we will move to an address. Let us take the address as 1000. So in this address there are some address. So first we will go to the address 1000. So inside the address 1000 we are having a value 2000. So 2000 is not our destination value. This is the address. So we have to move to the address 2000. So the value that is present inside the address 2000 is our actual value. So 10 is our actual value. So this is indirect addressing mode. So first we will go to a location. Inside that location we will have an address. So we have to go again to that address to fetch our real value. Next, immediate addressing mode. So in immediate addressing mode, the value of the operand is provided in the instruction itself. So that's all about addressing modes. So totally we are having 7 different addressing modes in our VAX architecture. Next hardware feature is instruction set. So our goal, the goal in VAX architecture is to provide an instruction set which is symmetric with respect to data type. So here we are having certain mnemonic format for each and every instructions. For example, prefix. So prefix of an instruction always specify the type of the operation. Suffix of the instruction will specifies the data type of the operands. Then modifier is there. So modifier will specifies the or gives the number of operands. So this is the specified instruction format. Prefix, the type of the operation, and suffix denotes the data type of the operands, and modifier will denote the number of operands. Example, let us take a specific instruction, add W2. So as per the instruction format, suffix add. So this will denotes the type of the operation, that is addition operation. Then suffix will denotes the data type of operation, W. So W is word. So our data type is word. Then a modifier is there which will denotes the number of operands. So 2 denotes 2 operands. So we are adding 2 word operands. Next example, mul 3. So mul is our operation, multiplication operation, and L denotes long word, and 3 is the number of operands. That is, we are multiplying 3 long words. Another example, CVTWL. So CVT denotes conversion, and we are converting long word, one long word to a word. Operands may be located in register or memory or instruction itself. Some operations are very complex. Hardware realization of frequently occurring code sequence implemented as single instructions. The advantages of implementing as a single instruction is it could be used for saving the designated number of registers. It passes list of arguments to procedure. It maintains stack frame, argument pointer. Then it also set a mask to enable error traps for arithmetic operations. So these are the advantages of implementing the frequently occurring code as a single instructions. That is, the number of registers could be saved. Then we can maintain the stack and argument point, and we also can catch the error occurring during the arithmetic operations. So the last hardware feature is input and output. So input and output operation is performed by input and output device controllers. Each controller have set of status and control registers and also data registers which are assigned locations in physical address space. The portion of address space where I/O control registers are mapped is called I/O space. That is, if this is our memory, the portion of the memory which is involved in I/O operations is called as I/O space. So in I/O space, we are having I/O control registers. To access the registers in I/O space, no special instructions are needed. I/O device drivers issues commands to device controller by storing values into appropriate registers. Software routines reads these registers to obtain status information. So this is handled by MMU, Memory Management Unit of our operating system. So that's how an input and output operation is performed. We will be either storing some data into the registers present in the I/O space from the device to the registers, or from the registers to the device. In that manner only input and output operations will be performed. So that's all about the 6 hardware features in our VAX architecture. So in our next class, we will be seeing about the next kind of CISC architecture, that is Pentium Pro architecture. Thank you.